Welcome to Study Loop.
Here we have a compound interest problem, and we're going to do part A mostly with the non-continuous compounding formula. And so we have an amount invested, $3,000, an interest rate of 5%, so we'll use the decimal 0.05, and a time of 5 years. So to find the final amount, if interest is compounded annually, which would be n equals 1 time per year, we have A equals 3,000 times 1 plus 0.05 over 1 raised to the power 1 times 5, and we put that in a calculator, and we get, rounded to the nearest penny, $3,828.84. Now we move on to the second part of part A, and we're going to calculate it for semi-annually, which would be 2 times a year, so n equals 2. So A equals 3,000 times 1 plus 0.05 over 2 raised to the 2 times 5, which would be 10 compoundings in the 5-year period. And we put that in a calculator, and rounding to the nearest penny, we get $3,840.25. For the third part of part A, we're going to calculate for monthly compounding, so that would be 12 times of compounding per year. So we have A equals 3,000 times 1 plus 0.05 over 12 raised to the power 12 times 5, which would be 60 compoundings. And rounded to the nearest penny, we get $3,850.07. So we can see the amounts are going up a little bit each time as the number of compoundings increases. For the fourth part, we're compounding weekly. There are 52 weeks in a year, so n equals 52. So we have A equals 3,000 times 1 plus 0.05 over 52 raised to the power 52 times 5. And that's going to give us $3,851.61. And for the fifth part of part A, daily compounding, we'll use n equals 365. So we have A equals 3,000 times 1 plus 0.05 over 365 raised to the power 365 times 5. Put that into a calculator, and we get $3,852.01. And for part 6, we're going to switch to continuously compounded interest. So we have a different model for this. We have A equals A naught times e to the RT. So that's going to be 3,000 times e to the 0.05 times 5. And we end up with $3,852.08. Not a lot more than the previous one, but it's the highest you can get for continuously compounded interest compared to any of the other compoundings. Now for part B, we're to find the differential equation that fits the situation. So because we have this basic exponential growth type model here, it fits the differential equation rate of change of A is proportional to A. So rate of change of A equals K times A. Now we know the value of K will be our rate, and in our equation we had A equals 3,000 times e to the 0.05 t, so the rate was 0.05, so that's our K. So now we have dA dt equals 0.05 times A, and we can go ahead and substitute our equation in for A, and we have 0.05 times 3,000 e to the 0.05 t. All right, let's multiply the 0.05 and the 3,000 together, and we get 150 e to the 0.05 t. So that's our differential equation for this situation. And for the initial condition, that would be what's the amount when the time is 0. And we know the amount invested was $3,000. So at time 0, the amount is 3,000. That's the initial condition.